It looks like you're over your NyQuil hangover.
Yes, I'm a little more alert and my cough is minimal. My cough is minimal. I'm very fortunate I have a brother that's a doctor, and I finally called him and I told him about my problem, and so he prescribed for me, of all things. I thought he was just going to give me some cough medicine, but he prescribed for me a nebulizer treatment, a breathing treatment. And I don't even use a nebulizer, but we have one here at the house because we have a family member with asthma. So we keep a nebulizer around the house for when that family member visits. And anyway, my brother prescribed some medicine for me to use with the nebulizer. And like that, my cough went away. So I said, man, I guess you do know what you're doing. I trust all doctors but my brother. I'm not so sure about him.
It's a
I mean,
sibling thing.
right? Is it? Is it? It's like
Mm,
he trusts all
very
teachers.
much so.
He trusts all teachers except his sister.
I trust all nurses but my sister.
Yes, we're not so sure about them. We've seen them at their worst. Okay. So, all right. Looks like we're all checked in. We're recorded. So, I'm going to share with you. Did the PowerPoint come through?
Yes.
Perfect. Okay. So, you should be looking at my PowerPoint now on your screen. And I'm going to go through a couple of these slides and talk about what we're looking at, what our topic is today. So we're going to change a little bit and not so much talk about chemicals, but we're going to talk about light of all things. We're going to talk about light. Now, the reason that we spend some time talking about light is because we're going to eventually compare the properties of light with the particles of matter, and we're eventually going to get back to talking about atoms. And so this is kind of all of a sudden, this part of the semester is like, where are we talking about all of a sudden things that don't even seem like chemistry? If you've had a physics class, this next lecture will sound a whole lot of like quantum mechanics from your physics class. So there's a little bit of physics that overlaps with chemistry, and this is that part. So we're going to look, if you're following along, have slides 2 and 3 handy. Those are the ones I'm going to look at right now. So chapter 7, quantum theory. This is chemistry. And today is the 12th. So some of the people that we're going to talk about, a little bit of, quantum mechanics, quantum theory. We're going to be mentioning people like Max Planck. We're going to hear about Hund's rule. We'll talk a little bit about the Heisenberg principle. Those of you that are fans of Breaking Bad, that's, yeah, that Heisenberg principle. And then we'll talk about quantum numbers. And then the part that people usually remember, electron configurations. But these are the highlights that I'm going to talk about from this chapter. And so to start this all kind of together, we're going to talk about the properties of waves. Talk about the properties of waves. So if you have a wave, okay, and this is kind of like you're looking at a screen of some oscillations. If you look at a wave, you'll see, something like this. And we'll go ahead and finish it out. There we go. And one of the things that you hear about when you talk about a wave is the wavelength. So this is a peak. And then if I draw it out just a little more, I'm going to draw it out a little bit more. This down here, this is a trough. So the peaks are the high parts above this line, and the troughs are the low parts below this line. So when we talk about a wavelength is from peak to peak, or it can be trough to trough. So from here to here is one wavelength. And we use the word or the Greek symbol lambda. Looks like an upside down Y. That is the symbol for a wavelength. So it's peak to peak, or it could be trough to trough. That is a wavelength. Now the amplitude, that is the height from the midline. So this right here, this line is the midline. So this could be considered the height. So could this, by the way. That could also be considered the height. So the height is basically the distance to either the peak or the distance to the trough from the midline. We consider waves to be like moving. So if this was an electronic device and I had some waves that were moving, and I have a little thing to show you here of some moving waves. Let me bring up my wavelength. Oh, that's not it. But if this was moving, like if I had it on an oscillation machine and I could see these wave moving, then I could talk about the frequency of a wave. And frequency is symbolized by the Greek letter nu. You pronounce that nu like not old, but new, but it's spelled N-U. And it looks like a letter V. It looks like a letter V. This is lambda. This is nu. And the frequency is the number of waves that pass through a particular point per second. Now, when we talk about the speed of a wave, okay, we can actually calculate the speed of a wave, and we use a letter U for that one. The speed of a wave is equal to the wavelength times the frequency. So wavelength times frequency. We can calculate the speed of the wave. Oh, something I forgot to mention about wavelength. It's usually measured in cycles per second. And the most common way that we measure that is what's called hertz, H-E-R-T-Z. Hertz is equal to cycles per second. And hertz is usually abbreviated HZ. And you pronounce hertz like, you know, you fell down and and something hurts. You know, I hurt my leg, now it hurts. That's how it's pronounced. So looking at our diagram, our PowerPoint, this is kind of what I've explained here. This is a diagram showing um, the parts of a wave, but this is what I wanted to show here. These are two different waves. Here's a wave on the top, and here's another wave on the bottom. You can compare the wavelength and the amplitude of two different waves. So on this diagram at the top wave has a long wavelength, whereas the wave on the bottom has a shorter wavelength. What they have the same, however, is they have the same amplitude. It's kind of hard to tell. It looks, because this picture is so small, but again, we're playing with these new terms to us. The height of a wave from the midline to the peak is what they're using as their definition of the amplitude, but it could be from the midline to the trough. That's also the amplitude. But these two waves have the same amplitude, but this has long wavelengths and this has short wavelengths. If these waves were moving, what we would see is that the bottom one has a higher frequency than the top wave. So usually there's a relationship where that you have shorter wavelengths have a higher frequency. So in other words, this would have more cycles per second passing through a point than what the longer wavelengths would be. And generally speaking, higher frequency is associated with a higher speed. So long wavelengths usually have lower frequency, slower waves. High frequency, shorter waves, but a higher speed. So let me write that out for you. So just generally speaking, longer wavelengths equals slower frequency. Equals slower speed. Shorter wavelengths equals a faster frequency equals a faster speed. It's just a rule of thumb. It's a rule of thumb. So what do we do with these ideas of frequency and amplitude, and why is this important? Okay, why is this important? Well, there's something called electromagnetic radiation. Okay, something called electromagnetic radiation. And what this is this is the emission and I guess transmission, put that in there too, the emission and the transmission of energy in the form of these waves. And I always like a definition inside of a definition. That's my favorite. So what is an electromagnetic wave? What is that? Well, this is an electromagnetic wave. It has an electric field and a magnetic field. So it's made of an electric field, and a magnetic field. And so if you're following along in your textbook, you can look at a diagram, page 277, figure 7.3, that shows a picture of what we mean by electromagnetic field along with an electric field and a magnetic field. And let me see if that is in your PowerPoint. I'm not sure if that's in your PowerPoint. Let me check. If it is, I'll tell you what slide to look at. Oh, it is. It's slide number 3. Let's look at the PowerPoint. Okay, so slide number 3. So here's what we mean by an electromagnetic field and a magnetic field. When you have these waves, now this is on an X, a Y, and a Z plane. So if you look here, here is the Z plane, here's the Y plane. I'm sorry, this is the X plane, here's the Y plane, here's the Z plane. So we're talking three-dimensionally. Electromagnetic fields are at right angles one to the other. So your electric field has waves, in a sense, passing through it. And then at right angles, your magnetic field has the waves kind of passing through. So when we talk about visible light, light that we can actually see, it has both the electric field component and the magnetic field component. So we say that light is an example of an electromagnetic radiation or an electromagnetic wave. Light in general, as discovered here, travels in a vacuum at a speed of about 3 times 10 to the 8th meters per second. That, by the way, is a number you should know. That's a number that you should know. The wavelength of, or the speed of light in a vacuum travels at 3 times 10 to the 8th meters per second. All electromagnetic radiation, when it travels at the speed of light, there's a relationship to it that it's the wavelength. There's that lambda times its speed, nu. Looks like a V, but remember that is nu, is going to be equal to the speed of light in a vacuum. And I think, yeah, we do. So let's kind of make use of this little, let's make use of this new equation here. We're going to look at slide number 4 is also example 7.1. Those of you that are following in your book, on page 277. So making use of this new, oh, if you need to write this down, lambda times nu is equal to the speed of light. So the wavelength of green light from a traffic signal is centered at 522 nanometers. What is the frequency of this radiation? So I'll let you write this down, those of you that don't have your book open. All right, so how do we solve this problem? So here is our equation. We're going to rearrange it to solve for v. So v is equal to the speed of light divided by lambda. All I did was move lambda over here by c. And then our solution, we are given that lambda is equal to 522 nanometers, because it says the green light from a traffic signal, it's centered at 522 nanometers. What is the frequency of this radiation? Well, we're going to have to convert this nanometers to meters. And so we'll do a quick conversion here. 522 nanometers. And the conversion, and we use a lot of nanometers when we're talking about electromagnetic radiation. The conversion is 1 nanometer is equal to 1 times 10 to the negative ninth meters. So a nanometer, the nano prefix is 10 to the negative ninth. So all we're doing here first is we're converting nanometers to meters. When we do this conversion, we end up with 522 times 10 to the negative, 5.22 times 10 to the negative 7th meters. Okay. We're not done yet. We're just getting ready to substitute. So now using the speed of light, and I'll write that over here in case you forgot, the speed of light is 3 times 10 to the 8th meters per second. So using our speed of light, nu is going to be equal to c, which is 3 times 10 to the 8th meters per second, divided by the value of lambda. That's what this is. All we did was we converted it to meters. That's why we had to convert it into meters, is because we needed to be able to divide meters by meters, giving us with seconds or cycles per second, which would be a hertz. So 3 times 10 to the 8th divided by 5.22 times 10 to the negative 7th. Even though if you're following in your book and if you're following in the PowerPoint, they do give you the answer to this. What I want you to do is to practice putting these numbers into your calculator. The reason is because when you put numbers that are in scientific notation in your calculator, and then you have to add a negative sign, make sure that you're comfortable adding these into your calculator. So I'm going to put, and I use parentheses. Your calculator may or may not have you use parentheses, but I'm going to use parentheses on mine. 3 times 10 to the 8th. And make sure that when you put this into scientific notation, you're using the scientific notation button. You're not using the big X, the big multiplier. Divided by 5.22. On my calculator, it's a second function. It looks like two big E's. And then on the negative 7th, I don't want the subtract sign. I want the negative sign. Then I'll close my parentheses. And my answer looks like, I don't know if you can see it very well, but my answer is 5.74, and then up here, over here in the corner, times 10 to the 14th power, which matches what my textbook says. But this is in hertz because it's cycles per second. But I wanted to take the time to make sure that you're punching the correct buttons on your calculator. Before I move on, does anybody need help figuring out what the buttons are on their calculator in order to enter this correctly? Type a number 1 if you're good. Type a number 3 if you have no idea how to enter this into your calculator. So 1 if you're good, a 3 if you have absolutely no idea. Gage, what kind of calculator are you using? Isaac, what kind of calculator are you using?
I have a TI-84.
Okay, you have a TI-84.
Yes, ma'am.
Somewhere on your calculator, Gage, you have a 30. So Gage, you have the same calculator I do. All right, Isaac, somewhere on your calculator, and I don't have an 84 with me, but you're going to have this same button right here. This is going to be your negative button. Somewhere on your calculator, you're going to have a second function that says the two big capital E's. It may be like on yours, you just can't see it very well on mine, but it may be on your calculator the second or even the third function of your x to the negative 1 button. So Gage, watch me again and do the same thing that I do, because you and I have the same calculator, Gage. But Isaac, did you find those buttons on your calculator?
Yes, ma'am, I did.
Okay. So Gage, I recommend using your parentheses. You don't have to, but watch me again, Gage. So I open my parentheses. Now I'm typing in the number 3. Now I'm going to use the second function and then x to the negative 1, and that's going to bring up a little e on my display. Isaac, yours should bring up a little e on your display too, because that means you're in exponential notation. And then use the negative button, not the minus, not this one, but use the negative button. Oh, we don't need a negative button yet. Sorry, I'm getting ahead of myself. If you see this on your display, that literally means 3 times 10 to the 8th power. Divided by, now open your parentheses again, 5.22. Now we need to do the exponential part. Second, Gauge, again, use the second, the x to the negative 1 button. That'll bring up that little e. Now you use your negative sign, 7. So both of you, your display should look just like mine. Your display should look just like mine. Even though you're using different calculators, your display should look just like mine. And when you type that in, you'll get this big long number, but Gage, look all the way over in the corner, you'll see a little tiny 14. And if you look real close, you'll see a little times 10 down here at the bottom. It's not showing up on the camera, but you would read that number 5.75, if you rounded it up, times 10 to the 14th power. Isaac, were you able to get this answer?
Yes, ma'am, I got it.
Good, good. Gage, are you doing okay? Oh, okay, you got it now. Thank you. Good. I wanted to make sure, because when you do the quiz for this chapter, there's going to be some calculations that you have to do like this, and the math is not hard. The most challenging thing is entering the numbers correctly into your calculator. All right. So how does electromagnetic radiation apply to us every day, so to speak? So I'm going to go back to the PowerPoint. This is slide number 7. Those of you that are following in your book, this is page 278. Slide number 7, page 278. So in short, everything that has electromagnetic properties or has electromagnetic waves as a part of it is part of what we call the electromagnetic spectrum. And the electromagnetic spectrum measures wavelengths, and I'm going to show you right here, measures wavelengths from about 10 to the negative 3rd nanometers in length, all the way up to 10 to the 13th nanometers in length. Over here on the left end, these are really small. Over on the right end, these are large. So if you want to get an idea of, how big are these waves, well, this is super tiny, and this is much, much larger. that corresponds to frequencies or hertz. If you notice, here is very small waves, very high frequency. Remember, I told you that at the beginning, short waves, high frequency, high speed. Look at the frequency, it's 10 to the 20th. But if we look at the opposite end, 10 to the 4th, that's a relatively low frequency, but we have the longest waves. Now, what do we experience as the electromagnetic spectrum? What is it that we actually see? Well, visible light is a very tiny part of the electromagnetic spectrum. Our eyes, literally the retinas of our eyes, by the way, if you're looking for a presentation or for a topic for your oral presentation in lab, those of you that went to lab last week and I talked about the oral presentation, if you're looking for a topic, the electromagnetic spectrum and how it relates to biology, but remember to emphasize the chemistry part. This is a really cool topic. You know, how your eyes work with respect to electromagnetic spectrum. Our eyes, and I mean human eyes, not mammalian eyes, but our eyes, human eyes, our retinas are designed so that we can only detect, or those of you that are in biology, our neurons fire whenever we are bombarded with frequencies between 400 and 700 nanometers in length. That's how we see color. We literally respond to electromagnetic energy bombarding the cell membranes of our neurons that comprise our retinas, our rods and our cones in the back of our eyes. 400 nanometers in length, that's towards the short end, or the low wavelength, I should say, or the high wavelength, and the 700, the red colors, that's more towards the long wavelength or the lower frequency. If our eyes worked more like that of an insect, insects can actually see beyond what is on this little diagram here. They can see into the ultraviolet part of the electromagnetic spectrum. So things like bees, wasps, but bees are a great example. How they see flowers and how they can find pollen is because their eyes work better over here and they interpret the colors of petals of flowers in order to find pollen. Things like snakes and mammals that can see in the dark much better than what we can. If you're wondering how can they see, it's because their eyes work better in the infrared area of the electromagnetic spectrum. So if our eyes, our human eyes, were designed a little differently, we could actually see at night, we could do heat detection and we wouldn't need basically night vision goggles, which is what they detect as heat vision in a sense. Isn't that cool? But outside of the visible light spectrum, here towards the higher frequency, the shorter wavelength, you have gamma rays and X-rays and ultraviolet rays. Make a note of this either in your textbook or on your slideshow. On this diagram, gamma rays have the highest frequency, the shortest wavelength. They are the most penetrating type of energy on this diagram. So gamma rays, very, very short wavelength, and that allows them to penetrate just about anything. They are the most energetic type of waves. That's why they're so dangerous. Slightly less energetic, slightly less penetrating are X-rays. Literally like when you go to the doctor and you get an X-ray of a bone, X-rays, X-ray machines, what they do is they use light, but at a different frequency, roughly 10 to the 18th, in order to penetrate soft tissues. This is why also you can take X-rays with your clothes on. The X-rays penetrate through your clothing and through your soft tissues, but they do not penetrate through the density of the bones. So they reflect back and you get these shadowy images of the bone tissue. if we had eyes like insects, we could see ultraviolet rays. Things that are ultraviolet would be those of you that worry about wearing sunblock because you don't want to get sunburned. The waves from the sun, which cause sunburn, the UVA and the UVB rays, their frequency is in this area of the diagram. And so the sunblock that you put on your skin, by the way, again, if you're looking for a topic for your oral presentation, the most sunblocks have little tiny micro pieces of metal mixed in with the lotion, which block the penetrating rays of the ultraviolet rays of the sun. The lights that you have in your house, the reason you can see light coming from your light bulbs, and if you have things like sun lamps or growing lights, we're starting to approach visible light in here. And then this is where we can start to see the colors of, like, you know, the color of your t-shirt, the color of the sky, the color of the grass, the color of your favorite lipstick. All of these colors are basically different frequencies within the electromagnetic spectrum. If your eyes, again, worked more like that of the eyes of a snake, you could actually see the waves coming off your cell phones and the waves coming out of your microwave oven in your house. You would even be able to walk outside and just using your eyes find an internet hotspot because you could see the waves coming out from a location. Isn't that crazy? You would even be able to see the waves coming off your car stereo. And I don't know anybody that uses a VHF TV now. Most people use internet TVs, but if you had a VHF over-the-air TV, you could actually see your television antenna making contact with those waves. Isn't
My
that
mom
great?
actually has that VHF TV.
Your
But
mom has a VHF, so she does over-the-air antenna?
yeah,
Does she get good reception?
no.
Oh,
No,
your poor moms. We need to start a GoFundMe page for her.
right? But she won't give up that TV because it was my grandma's.
Oh my goodness. Oh
Mm-hmm.
my. If your grandma was here, she'd be like, Mija, buy a new TV.
I know. We got her the plasma, like the flat TVs, the smart TVs. She has everything else but in her room, that TV has to be there.
Ah, well, it's comforting. It's
Yeah.
comforting. All right, so I'm going to show you a short video. This is the first one from Professor Dave, talking a little bit more about wavelengths, electromagnetic spectrum, and I mentioned Max Planck, talking about some of the contributions that Max Planck contributed to this idea of the electromagnetic spectrum and our understanding of light and waves in general. So I'm going to switch over to the video. Okay, let me know, yes or no. Do you see Professor Dave on the screen? Kind of a long-haired hippie looking dude?
Yep.
That's him. All right, so here's the video. It's not very long. It's about 4 minutes in length.
Hey, it's Professor Dave. I want to tell you about wave-particle duality. He knows a lot about the science stuff. Professor Dave explains. So let's take a break from atoms and look at something else, light. For some time, we had known light to behave as an electromagnetic wave. For this reason, light is also called electromagnetic radiation. Light waves have both a wavelength, the distance from tip to tip, and a frequency, the number of waves that pass by a point per unit time. They are inversely proportional, since the shorter the wave, the more of them that can go by per second, resulting in a higher frequency. These variables are related by the following equation, in which c is the speed of light, about 300 million meters per second, the speed limit of the universe. The electromagnetic spectrum shows light of all the different wavelengths, from gamma rays to radio waves, including this tiny sliver in the middle, which is visible light, the light we can detect with our eyeballs. The wave theory of light was very useful for a time, but it could not explain the photoelectric effect. This was the observation that if a certain metal plate is irradiated with light, an electron is ejected, which can be detected when it interacts with a positively charged wire or plate sensor. The incongruity was that the ability of the light to eject an electron depends only on its frequency and not its intensity. So if the beam was below a certain frequency, even a very intense beam with a lot of light could not eject an electron, whereas above a certain frequency, the faintest beam possible could do it. This seemed strange, and a famous fellow named Albert Einstein solved the problem by extending a concept developed by Max Planck just 5 years prior. Planck proposed that energy is not continuous, but rather is quantized. That is, all energies are multiples of the smallest fundamental unit of energy, the Planck energy. In fact, quantum theory went on to show that everything is quantized, space and time too. So you can't infinitely subdivide them. You'll eventually get to a smallest thing that can't be divided further. But more on that in the physics course. Einstein extended what Planck said about energy and rationalized that light must also be made of quanta, which he called photons. These are particles of light. This explained the photoelectric effect because an electron is ejected when struck by a singular photon with sufficient energy. It only takes one photon, so even the faintest beam above a certain frequency will be able to do it. But if none of them are of that minimum energy, no matter how many photons strike the sample, an electron will not be ejected. It was found that the energy of a photon can be given by the following equation according to the frequency of the photon and Planck's constant. We now have to accept that light obeys wave-particle duality, meaning it is both a particle and a wave at the same time. Confused? You should be. This is the first discovery in a series that brought about the quantum revolution, completely changing the landscape of physics and how we view the universe. Newton's laws no longer reign supreme in the world of the very small, and the universe became much stranger almost overnight, thanks to Einstein and others that were inspired by him. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Thanks, Professor Dave. Let's see, where is my... Oh, how do I take this off? Okay, now I can't get the video off. There we go. Okay, so what Professor Dave was talking about correlates to, this is slide number 8 that I shared in the slideshow with you today. This is slide number 8, this idea of the heated solids problem solved by Max Planck. In other words, what scientists eventually put together was this idea that wave particles travel in small packets of energy. Planck, and I've never heard him called Planck, Max Planck, and I don't want to argue with Professor Dave, but I'm going to pronounce it Planck. Max Planck, he coined the term photon to describe bursts of energy that we could see coming off of this heated solid. And basically what he did was he heated a solid by bombarding it with energy and then watching individual electrons come off. If we skip ahead quite a few big ideas, this is how it relates to light. We know that light has a dual nature. It behaves as a wave and it behaves as a particle. So Max Planck coined the use of the term, Einstein coined the use of the term photon to describe a particle of light. So light is not continuously emitted. It's emitted in like little tiny bursts or little tiny packets of energy. When this was first proposed, this literally kind of revolutionized the idea of, as he mentioned in the video, the idea of how we understood light. Some people thought light was wave-like. Some people thought light was particle-like. turns out light is both. That means that it almost behaves like matter, even though it's light. Can you imagine having a box of light? You can have a box of air. We can't see air, but you can weigh air and you can compress air. Air is a particle. But can you imagine weighing light or having a box of light? You can't weigh light and you can't compress light, yet we still, in a way, say that it behaves like a particle. It has mass-like properties. I'm going to stop here because I need to end today's lecture a little bit early. But as I mentioned at the beginning of the lesson, what I want you to do is I want you to watch 3 more videos which correspond to the rest of this lesson. And those videos are already posted in Blackboard under this week's folder, under the April 12th heading, under the web links. And it's the Bohr model of the hydrogen atom, quantum mechanics, and quantum numbers. I'll review this information with you on Wednesday, but I would like you to use the rest of today's time to watch the videos, or at least watch them between now and Wednesday. All right, do you have any questions for me?
No, ma'am.
All right, if not, I will see y'all on Wednesday. Thank you for your attention for today. Y'all have a nice afternoon. Oh, by the way, we do have lab today. It is our last regular weekly lab meeting. So those of you that come to lab, or I'll still see you today at 2:30. Those of you that do the lab on your own, be prepared that this is our last regular weekly lab. I can't remember the name of it, but also check your course messages in Blackboard for lab, because I'm going to be sending you the information about the oral presentations. I forgot to send them last week, but I talked about them in lab last week. I'll send the information today. All right, you guys have a nice afternoon. I'll see some of you at 2:30. I'll see the rest of you on Wednesday at 10 a.m. Thank you.
Bye.
Bye-bye.